This is a production of Cornell University.
It is a pleasure to share with you for the first time part of my research work. The title of my talk is Identifying Potential Heterotic Group in Nigeria Cassava using data from IITA breeding program. Cassava, my favorite crop, belongs to a family of Euphobiaceae, that is flowering plants. It is predominantly classified as outcrossing species, despite having both male and female reproductive organ. It is clonally propagated crop. Cassava is extremely heterogeneous. Because of this heterogeneity nature of this crop, to improve the performances of population cross is always a big challenge in identifying the optimal parental combinations. But one possible way to address this obstacle is to use reciprocal recurrent selection, through which you can identify two heterotic groups to optimize the performances of the cross. So there are three main objectives of this study: to estimate additive and non-additive genetic variants and assess their predictive ability in genomic prediction. So the result from this objective will be used to simulate progeny from parental combination, knowing very well that to evaluate thousands of progeny from a pair of cross is always impractical in the field evaluation. So there's need for us to do simulation. So based on the simulation, we are going to use the result to predict genetic merit of parents toward identifying heterotic group. So this is the general concept of the whole study. So we tend to have two populations: the training population. So this will consist historical data from next-gen project in IITA breeding programs. So we are going to use those historical data to predict the performances of the progeny simulated from the candidate population. For the candidate population, we have to start by identifying existing germplasm in the breeding program. From there, we are going to simulate half the allele among the clones. So we are going to simulate 100 progeny per family, and we are going to predict their performances by using the historical data from the training populations. So based on the main performances of those progeny and their genetic similarity, we are going to classify them into two heterotic groups. So what is new? So we have started to pull a number of trials together. So we have a total number of 38 trials across different evaluation stages: clonal evaluation, preliminary year trial, advanced year trial, and uniform year trial across two locations, Ibadan and Ikenne. So we have a total number of 7,342 data points. So we still have SNP data. So there's need for that in order to capture the segregation among individuals within the same family. So after doing all the quality checks, so we end up having a training population size of 684 samples by 12,317 SNP marker. So we do all sorts of analysis using different kind of applications. So one of them is Soma Library in R. So to start with, the traditional practice for you to analyze data is to do some exploratory analysis to have idea of what your data looks like. So this is the box plot and histogram showing the distribution of fresh root yield. As you can see, the data seem to approximate normal distributions, except that of clonal evaluation, which is a little bit skewed to the right. As you can see, the point, which is the mean, is a little bit higher than the median. So for the SNP data, you know it's always characterized with erroneous value due to how that data is sequenced. So this is the pipeline we follow to get rid of erroneous values. So we filter based on site missingness, manual allele frequency, filter low depth samples, mean depth sites, and the threshold I use is the one in parentheses. So after filtering the data, so we have to impose this clean data using Beagle. So I also use Blink to convert it to dosage formats, and there's need to have APMA formats so that we can use that to get the genetic distance. So this is the detail of how we went about cleaning the data. Cassava being a diploid organism, it has the SNP data is biallelic. So this is the frequency of the first allele, frequency of the second allele. So we use we filter for manual allele frequency using 1%. And for the site missingness, we use threshold of 10% so that those sites that have 10 and above across the sample should be removed. Likewise, we do the same thing for the sample. So we use a threshold of 10% so that those samples that have 10% and above missing data across the sites should be removed, should be excluded. For the site depth, the depth here is the number of sequence reads per site. So we use threshold of 10 and 100 so that those samples between 10 and 100 should be retained. So those below 10, those are the sites with low sequence error. So there are some sites that have high depth due to probably repeat region. So those ones are also eliminated. So we are interested in this region here. So after all these filtering criteria, so we end up having 962 samples by 12,317 markers. So having got the clean SNP data, so I use Soma library in R because it has a kernel to extract the genomic relationship matrix. So using the formula adapted from Endelma 2011 and Faraday 2008. So this is the relationship matrix. As you can see here, so the question is, from these three components of epistasis, which ones will I use in my models? So I try to come up with these correlation matrices by extracting up diagonal elements. As you can see, additive by additive is has the least covariance with additive and dominance. So I try to use this. But some may argue, why do you have to use additive by additive, knowing that cassava is an outcrossing species? So unlike self-pollinated crop like wheat, where additive by additive is well pronounced. I'll talk more on that later. So to start with the analysis of the data, I use two-stage approach. So the first approach is to analyze the phenotypic data. So from the clonal evaluation trial, this is the model I use. So clonal evaluation trial is early stage of breeding program where we have so many lines to evaluate, but because of insufficient planting materials, so we have to use checks. Checks have to be replicated in every blocks. And for the other evaluation stages, we have enough planting material, so we normally use randomized complete block design. This is the border fitted. So where the genotypes are taken to be random to estimate the genotypic variance, and this is the G-prop model fitted. So you can see this is the fresh sheet, this is the intercept part of the model, and this is additive effect. So the same thing for the, so we use this as a baseline model. So the other multiple kernel models, see, in addition to additive effect, we have dominance here, we have epistatic effect and dominance and epistatic effect here. So this is studentized residual from the phenotypic data, which is a very good statistics to detect an outlier. And this is the variance component estimated from those different evaluation stages. As you can see that the residual variance keep declining from early stage to later stage. And this is because at late stage of breeding, we have it's a kind of a trial with a large plot size. So having fitted those G-plot models, so the field statistics reveal that the model which incorporate additive dominance and epistasis seem to give the best prediction abilities. So as you can see here, and this is histogram showing the distribution of those prediction accuracy. So this is I try to partition the total variance, total genetic variance into different sources. As you can see here, the dominance and epistasis seem to contribute a very large effect. So meaning that we cannot ignore the importance of non-dominance effect, and which means that the model that has additive and non-additive is likely to give you good prediction for genetic merit. So the lesson learned from this lesson is that the model that include additive and non-additive effect predicts genetic merit accurately, and the dominance effect is not completely independent of additive effects. So meaning that they overlap. And dominance effects seem to play a major role in influencing fresh yield. So the future work is to consult with IITA research team to assemble the candidate pools from which the heterotic group will be defined. So I still need to explore other genomic prediction method to compare the result with the existing ones. So I need to simulate approximately 100 progeny for each pair of parental combinations. So I give special thanks to my special committees for their support, for their advice from time to time, to all the members of John Lowe Group, friends, for advice in one way or the other. Thanks to Bill and Melinda Bill Gates, UK Head, for the financial support toward this research work. Thank you all for listening.
Take any questions?
Have you tried fitting these models? So you do the additive fit, and then you add a dominance kernel, and then you add an epistatic kernel. Have you actually tried to fit just a dominance or just an epistatic and compare that to the additive itself? Okay, yeah, so the question is, so you have this thing where you're doing like a nested, right? So you start with an additive only, then you have an additive plus dominance, and then you have additive plus dominance plus epistasis. My question is, have you tried to fit just dominance or just epistasis? It's been my experience that you end up with really similar prediction, at least in an inbred. By modeling only epistasis, I end up with really similar prediction accuracies as the additive.
The only thing I try to do is, I did that early this morning. So instead of using the additive by additive as epistatic components, I try to use additive by dominance to see what is going to happen. But what I observe is that the broad sense irritability is much higher, around 0.67. But when I look at the prediction accuracy, it's almost the same thing with that of additive by additive.
Yeah, that's because there's a big scale.
We have time for one more question.
This has been a production of Cornell University, on the web at cornell.edu.